Good morning, Miss Fiska and Dr. Noraziah.
Good morning.
Thank you for being here. Thank you all the students and all the lecturers for being in this seminar. In this today's seminar, we will have Dr. Noraziah Adzhar, Senior Lecturer of Mathematical Science from University Malang, Malaysia Pahang. She will share with us about application of integral. To help this seminar, there will be Miss Fiska Noviantri, Lecturer of Mathematics Department, Binus University, as the moderator. Without further ado, I will give the screen to Miss Fiska.
Okay, thank you, Miss Adzhar. Okay, good morning, doctor, and good morning for all Binusian. As we know that today we have a guest lecturer for international seminar with the title Application of an Integral as the implementation of the global learning system in Binus University for calculus courses. Maybe now let me introduce our guest lecturer first. Dr. Noraziah Adzhar got a bachelor degree in 2011 and Doctor of Philosophy in 2015 from University Technology Malaysia, Skudai, Johor. But now she is a senior lecturer in the Center for Mathematical Science at University Malaysia Pahang. She has teaching experience in various mathematics courses such as applied calculus, numerical method, basic mathematics, programming, and simulation. And her main research interest is a computational mathematics, routing problem, and graph theoretical application. Okay, doctor already here? Miss Ajeng, or not?
Yes, Bu Fiska. Assalamualaikum and hi everyone.
Waalaikumsalam warahmatullahi wabarakatuh. Nice to meet you, doctor, again.
Nice to meet you again.
Okay, how are you, doctor?
Alhamdulillah, doing good. But I'm trying to I'm trying to connect to two devices for this.
Okay.
Can I request for 3 minutes maybe?
Okay. And doctor, is it okay if the participant asking during session, or you may prefer at the end of the session for Q&A?
Up to them. Okay, I'm okay with any.
Okay. Okay. So for all Indonesian, if you have any question, maybe you just raise hand or may chat on the chat room, yeah. Let's wait our guest lecturer to prepare her device, yeah. Or maybe for all participants, can you open your camera?
Okay, Bu Fiska, I think I cannot to try using my iPad during the session, but again just using my laptop. Yeah. I think you are muted.
Oh yeah, sorry. Okay. Of course. Also, you only join with your device PC, right?
Yeah, using PC.
Oh, okay. But are you ready?
Yes, sure.
the session.
Mm.
Okay. Miss Noraziah, time is yours.
All right, thank you so much.
Okay.
Unfortunately, I cannot switch on my video because my Zoom is at my laptop is not working for the camera. Is it okay?
Okay, is it okay?
All right, okay, thank you so much. Okay, so I'm sharing my screen first.
Okay.
All right, Assalamualaikum, good morning, and hi everyone. Can you see my slide?
Yes.
All right, thank you. Okay, so actually this is the second time I'm involving with this GLS Mira. So the previous time is into 2022 for the same topic. Okay, but maybe so this time for different group of students client. All right, so my title for the seminar today is the applications of integral. So I am Noraziah Adzhar from the University Malaysia Pahang, from the Center for Mathematical Sciences. So thank you, Bhuviska, for the introduction from the beginning of the session. So have you been to Malaysia, students? Have you been to Malaysia or in Pahang specifically? No, not yet. So actually, I have been in Indonesia for 2 times, in Bandung, visiting the, sorry, not Bandung, in Surabaya, visiting the Institute of Technology 10 November, and then in Bandung for vacation. All right, so it's a nice country and I love to go again. Okay, so let's begin. So if you have any question or if you're gonna hear my voice or anything, you can just interrupt my session, okay? So this is a little bit about me. So I'd like to introduce my university, which is the University Malaysia Pahang. So we have 2 campuses. So the first one is Pekan campus, but previously the main campus is in Gambang. And then in 2009, we have another campus in Pekan. So this is the Pekan campus. Okay, and this is the Gambang campus. All right, so this is our portal, Center for Mathematical Sciences, just in case some of the students would like to pursue their study in Malaysia and would like to pursue their study in University Malaysia Pahang. So this is our website, Center for Mathematical Sciences, to see the opportunity. Okay, and this is the facilities. Actually, this is our building. If you can see my cursor, can you see my cursor? Can you or cannot see my cursor? All right, wait, I think. Okay, I'm using slide instead. Okay. So I think here you can see my cursor. Okay, so this is the facilities, the building of the faculty and the entrance. And we also have the Mathematics Support Center to help the students if they have problems in mathematics. We have one in Gambang and we have in Pekan campus. Okay, so we also had a lot of activities at this center. So some of it is back to basic to help students to recall their basic of mathematics in order to go for another advanced mathematics subjects, book donations, Sudoku battle, and so on. All right, and this is the research room and the computer lab for the postgraduate students. Okay. All right, so let's go to the applications of integral. So I'm I'm pretty sure that you have learned about the integral with your lecturer, with Bufiska, and with your class lecturers about the integration, differentiation, and so on. So before I'm starting, I would like to share a few example of calculus applications in real life. So not limited to engineering part. So whenever we talk about calculus, we always see that calculus in terms of engineering applications, in civil applications, in structural applications, so on. But we also use calculus in cancer in order to determine the growth or shrinkage of number of cells, and using exponential function, the oncologist can analyze the progression or the regression of a disease. In cardiology, we use differential calculus to determine the blood flow dynamics needed to build an artificial aorta model in order to make sure it is placed correctly during transplant. Okay. And competing weather patterns, so we use differential calculus also to predict the effects of the weather conditions with the parameter of temperature, humidity, and pressure changes. Spaceflight engineering, we need to use calculus to check the gravitational pulls of the sun and the moon in order to know how to launch a probe or hit the velocity needed to orbit the Earth. And the last application is maybe using the in economics. Okay, in economics, we can use calculus for the setting payment structures and the minimum due amount by the credit card company by considering variables such as the interest rates, the fluctuating balance, and so on. So these are some of the applications of the calculus, not limited to the engineering side. Okay. So you might be wondering, the same goes to my student in class. I'm teaching calculus as well here. So they have that kind of demotivation when they're studying calculus because they do not know exactly when they will be using the calculus. They say that, no, I'm not using the calculus during my in their career life, and but we do not know. Okay, we do not know the impact of learning calculus in our life, because calculus is a branch of mathematics. It helps us in our critical thinking, the problem solving skills. Okay, they can enhance our learning. Okay, our learning. Okay, so let's go through the applications that you learned that covered in your syllabus, which is the area, the volume, and I'm touching another one, which is the arc length. Okay, so let's go to the first one, the area. Okay, so the area, so you already learned about this. So if f is continuous on AB, so let's say when we are finding the integral of this function fx. Okay, this function fx, okay, this blue colored one, the integration from a until b respect to dx. So dx is the value, the limit for a and b is respective to x, so a until b. So when we are solving this integral, so let's say the value is 3, so the 3 is actually representing the area under the curve. Okay, provided that the curve is above x, and from a until b, so we get the area under the curve. Okay, area under the curve. So let's say you want to find the area under the curve, you can use integration to find the area under the curve. Okay, but not all graph will be on top of x-axis. Okay, will be on top on x-axis on the positive part. Okay, on the positive part of y. Some graph is below the x-axis. Okay, some of it is below the x-axis, and we have the graph that is above the x-axis. So for the above x-axis graph, when we are finding the integration from a until b respect to x, so we are getting the area under the curve. But for the case where the graph is below the x-axis, so when we are doing the integration from the value of c until d respect to x, okay, so we are getting the not below the curve or under the curve. Actually, we are getting the area above the curve. Okay, area above the curve. So because of the area is below x, so you are going to get a negative value when you are solving this kind of problem. We're going to get a negative value. Okay, so because of the position of the area of the shaded region below the x. So what do we need to do is to modulus, okay, to modulus the result so that we're going to get a positive value, because we know that area is always positive. Okay, so we are going to, we need to do the modulus for the end results. So that is the case for the below the x-axis graph, and we are getting the above the x-axis, the shaded region above the x-axis. Sorry, above the graph. Okay, it's not under the curve, above the curve. So how about this example? So we have the region bounded by the curve y equal to x cubed, y equal to x cubed, for x equal to -1 until x equal to 1. Okay, for this case, we encounter both cases. One is below the curve, one is above the curve. Okay, so we have one below the curve. So this part we're going to get a positive value, and for this part below, above the curve, so you are going to get a negative value. Okay, you're going to get negative value. So when we do the integration, we cannot integrate from -1 until 1 directly. Okay, from -1 until 1 directly, even though we are considering the same graph. Okay, because the shaded region is at two different kind of here. Okay, so the first part of the integral must be from -1 until 0, and then we plus with the integration of 0 until 1. Okay, so for the part of -1 until 0 of the same curve, which is x cubed, so we know that this one is below the x-axis, the graph appear below the x-axis, so we are going to get a negative value here. So because of the negative value, so we need to have the modulus for this part. And then we plus with the other part. So this one we're going to give us a positive value. Okay, so this is positive value. So this with negative value, a positive and positive. So we are going to get a positive answer as the resulted area. How if we forgot to put the modulus? You are going to get -1/4 here. And when you plus with this result 1/4, you are going to get 0. So the value will be cancelled out. Okay, so 0 means measure the difference between area, and area is no difference because they are of the same size. Okay, no difference because they are the same size. It measures the difference, okay, of the area of both areas. Okay, so the correct way is to put the modulus so that you can total up the area, okay, for both regions. Okay, so area between two curves. So previously area one between for one curve, but one is above curve, one is below curve. But now the area between the two curves. So between the two curves, we can see as two different parts. The first part is, okay, I need to use my pen. The first part is here, and another part is here. One is below curve, one is above curve. So for the first part here, your integration will be from a until b, and integrating the function fx respect to dx. Okay, for this part, the integration will be from a until b, the same integral, the same limit for a until b. For the gx function, because it's different function, gx, the green one, respect to dx. And we know that this one are going to give us a negative value. So we need to have, we can multiply with negative. We can multiply with negative so that we get a positive value. So because this part, the limit for both region is the same limit, we can combine. We can combine all together. So we can combine, pardon my writing, yeah? Combine, and we get this formula. Okay, fx minus gx, because they are sharing the same limit. Okay, it's different between these because they are not sharing the same limit. Okay, for this case, they are sharing the same limit from a until b, and we can do like this. So fx minus gx. So that's how you get minus inside your operations. Okay. Okay, let's try this one. Okay, can I hear some voice of the students? Hello, everyone.
Come on.
Hello, hi. I believe that the students here is a bachelor degree as informed by Buviska. Okay, can I ask you to try to develop, okay, not to solve, maybe because we have a not much time, okay, to do this together. So maybe to develop the integral to find the area of this region. Okay, so to do this, you need to understand few of the knowledge that I have shared before.
Come on, anyone to try to develop about the integral to represent this area?
Okay, maybe I can give you 5 minutes to try first, and then you can speak out your answer, or maybe you can share in the chat. Maybe you can share in the chat that we can. Oh, your answer here. Okay, okay, sorry, I did not see the chat. Yes, okay, all right. Okay, maybe you can share your answer here, so then you speak out the answer, so I can write here, and then we check together whether the development of the integral is correct or not for this exercise. Okay, any volunteer? All right, the area of the region.
Come on, anyone? Just only for the first formula for the area, right? Dr. Noraziah, not until the finish,
Yeah.
until the, only for the integral, the formula of the integral.
Okay, I received one solution here. The area of the region can be given by, I'm not sure who is this, okay. The area of the region can be represented by the integral of y equal to, okay, the integral, oh, sorry. Y, okay. Into two areas. Okay, I received two interesting answer here. So let's go through one by one. Okay, for the first one, we go to the first one. Okay, y equal to integration from 0 until 9. Okay, 2 square root x subtracted by the integral of minus the integral of x minus 3 from 3 until 9, and this is respect to the x. Okay. All right. So another one is, okay, should be divided into two areas. One is by calculating the definite integral of y equal to 2 square root x from 0 to 3. And the second one is by calculating the definite integral of 2 square root x minus 3 from x equals to 3 until x equal to 9. Okay, this is the first answer. And for the second possible solution is divided into two regions, isn't it? So 0 until 3 plus 3 until 9. Okay. For the first one, it is integration of 2 square root x respect to the x. For the second one is two square root x minus 3 respect to the x. Okay, thank you. Okay, other than that, okay, good. Thank you so much for participating, okay, in this exercise. So there are two possible solutions here, and both are correct, okay, and both are correct. So you can try to use this one, or you can also this kind of integration, okay. So for the first part, you find the area for the whole region from 0 until 9, and then you just minus with this triangle, okay, the area of this triangle, so you're getting the rest of the area. Okay, this one is quite pretty easy, okay, to do the integration. Okay, so the next one, you are dividing into two parts, which is the part A and the part B. So this is the A part, this one from 0 until 3, and the second part is the whole area here, and then lastly you minus with the triangle, so you get the remaining of the B part. Okay, the B part. So both are correct. Okay, so good job. Well done. Okay, let's go to the next one. Volume. Okay, so you are learning volume. How method you learn to find the volume? The first one is the disk method, disk or washer method, isn't it? So I think I have a lot other kind of method to find the volume by using the single integral. So what you are learning is a single integral, find the volume. So let's go to the first method, which is the disk method. Okay, the disk method is we imagine that a region is revolved, okay, revolved through a line in the same plane and resulting an object that is known as solid of revolution. So from a 2D graph, we revolve through the x-axis or about the y-axis, and we are getting a solid of revolution. So let's say for this one, okay, let's say for this one, so we have a curve y equal to fx, okay, y equal to fx. So previously we learned how to do the integration of fx from a until b respect to x. So what we're doing here actually, when we are solving this kind of integral, is actually from a until b we have a small dx. Small dx that can be represented by a rectangle. So when we are solving the integral, so actually we do the summation of the rectangle, the summation of the dx across the region from a until b. Okay, so as the dx getting smaller and smaller, so you are going to get a more accurate results. Okay, so this is the summation of the dx under the curve. So you are getting a value. So this one is called area. So we are going to imply the same concept for the solid of revolution. So let's say you have a curve y equal to fx. So we imagine that we revolve, let's say, through the x-axis. We revolve through the x-axis. So we are getting a few disks. A few disks. Okay, a few disks. So let's take out a disk. Let's take out a disk from this graph. So we have a disk, something like this. Okay, so the disk is, if we see from this part, we're going to get a circle. We see a circle. Okay, we see a circle. So the circle here, the area of the circle here, to get the volume of the disk, so we can multiply the area of the circle, which is pi r squared. We know that the area of the circle is pi r squared, and we multiply with the disk size here. So the size is dx. Some part of it is the dx. Okay, the dx across a and b. So pi r squared dx. Okay, so when we are integrating the pi r squared dx, we are integrating, same like this. So actually we sum up to all the disks across the solid of revolution here. So we sum up all the disks inside the solid. So we are getting the volume. Oh, sorry. Okay, we're getting the volume of the solid of revolution. So pi r squared. So what is r? So r here is this curve, isn't it? This is r. So r here is this curve. The curve is coming from y equal to fx, the function y equal to fx. So that's why the formula will be like this. The integral of pi y square dx from a until b, by y square dx from a until b. So it's coming from the understanding of the volume of a single disk, and we do the summation of the volume of the disk. Okay, so we get pi y squared. So same goes if we are finding the volume for an x equation, okay, an x equation, and we revolve or rotating a complete revolution through the y-axis. It will give us a solid symmetrical disk, and this is a disk. And when we do the integration, we are sum up the volume for each disk. So it will be pi x squared dy from C until D. So this is the case about y-axis, and this is the case about x-axis. Okay. Okay, for example, for this one, we have a semicircle for this function. Okay, so this semicircle represented by this function, y equal to r square minus x square under the square root. So about the x-axis. So let's try to use this method just now that we already learned from minus r to r. So we have pi y square, isn't it? So we have r square minus x square dx, pi r square from minus r to the positive r. So that is the volume or the solid of revolution. But when a semicircle will revolve through the x-axis, so what kind of solid we're going to get? Okay, what kind of solid we're going to get when we're rotating about the x-axis for the semicircle? Anyone in the chat? A circle, so we're talking about the volume, so you are getting a solid when a solid, okay? So a circle is not a solid. A ball, okay, did you mean a sphere? Okay, a sphere. Okay, let's check. Okay, so when we are solving this integral, okay, so all the way through the end, we're going to get 4 pi r cubed over 3. So actually we have derived the volume formula of a sphere from the volume by this formula. Okay, so when you revolve a semicircle, you get a full sphere. Okay, when you solve this one using a general value of r, you're going to get, you actually derive the volume formula of a sphere, which is 4 over 3 pi r cubed. Okay. All right, so this is another example where we have a curve y equal to x minus x squared between 0 until 1 about the x-axis. So when you revolve, you're not going to get a sphere because this one is not a semicircle. Okay, it's a parabola. So you're going to get maybe a shape more like an ellipse, maybe something like that, but not really an ellipse. Yeah? Okay, you get a solid. So solving this for pi times with x minus x squared from 0 until 1. So you are going to get a value of 0.1047. Okay. Okay, how about this one? Okay, can we do this together? Can I give you maybe 10 minutes? 10 minutes to do this. So we have a piecewise function from minus 0.5 until 1, and then from 1 until 3. Okay, for minus 0.5 until 1, we have this function. And for the value of x from 1 until 3, we have a different graph, which is of 1 over x. So first, we need to identify the region bounded by the graph and x-axis between x from 0 until x equal to 2. So we want to find the volume of the solid form when the shaded region in 1 is revolved at 360 about the x-axis. Okay, this yeah, can we try to do this? Okay, any answer? Is it integral 0 to 1 pi minus x minus 1 square plus 1 power 2, yeah. And then we plus with the integral of 1 and 2, 1 over x squared, yeah. This integral is correct. The solution given by your friend here is correct. Okay, but the difficulty of this question is to expanding. Okay, to expanding this one to the power of 2, and then to proceed with the integration. Okay. Anyone already getting the last answer? 2/3 plus ln 2. Okay, Christian, okay, can you share your answer here? Maybe you can send a file here so that your friends can see whether you do it correctly or not.
Anyone try to share your answer? Maybe only for the formula first. Anyone? Doctor, actually, our student not learn about the application of an integral yet because
Oh, I
already
see.
learn about the basic integral. So this is the first topic for them about the application of the integral.
Ah, I see. I thought they already learned about it.
Yes.
Okay. All right. Okay. Okay. So, yeah, I'm giving you the integral for this. So we have a 0 until 1. And then we have 1 until 3. Sorry, 1 until 2. 0 until 2. So 0 until 2. Okay, so the integration of 0 until 1 plus 1 until 2. So we were to find the volume. So pi times with the graph here, which is this one, minus x minus 1 square plus 1 square respect to dx, and then times with, okay, pi, and then integrate 1 until 2 pi, and then the graph here. So the graph here is 1 over x. So 1 over x squared respect to dx. So solving for this, you are going to get the volume of the solid revolution. Okay. So I think the solution is quite long for this because you need to expand and then you need to do the integration for each of the term. Okay. So solving this, you're going to get the volume of the solid. So I think I'm quite fast. I thought you already learned about the applications of integral. So I'm just showing the solution without trying to do with you altogether. Okay, so let's continue with the arc length, the third application, which is arc length. But I guess through today's session, you already learned about the formula. So after this, maybe you can do a lot more exercises regarding that topic and then try to use that formula. Okay, so the last one is arc length. So arc length is actually to find the length of a curve. Okay, the length of a curve. So a length of a curve from a specific point to another point that lies on the curve. So in order to do this, we might think of fitting a piece of string to the curve, and then we measure the string against a ruler. For example, for this kind of polygons, so we can put a string, the blue color one is a string, to try to measure the length of the curve, the arc length, all right, the arc length. So, but this might be not practical in many situations, especially when you have a complex curve. So that's why we need a precise definition and a precise method is needed that is applicable for any kind of curve, okay? So this is the formula from A until B. So we have the integrand, we call it as integrand here. So the integrand is the square root of 1 plus dy over dx squared. Okay, dy over dx squared from A until B. So given a function of y, whatever function, so first you need to differentiate. Okay, you need to find the derivative. So for the arc length, it requires two kinds of calculus knowledge, which is to be able to differentiate, and the second one is to be able to integrate. You have both, differentiate and integrate in one formula. So from the function given, from the curve, you need to differentiate first, and then you square all the resulted value, and then plus with 1 and all together inside under a set function, and then you integrate based on your point from x equal to a until x equal to b, for example, a until b. Okay, so that is the formula. So if this one is for you are given x equation, so it's just the same thing. If you are given the x equation from y c until y equal to d, so you need to integrate respect to dy, and the x equation you need to differentiate respect to y as well. So dx over dy is vice versa. Yeah? So this one is for y equation, and the integral is based on the dx respect to dx, and this is when you are given the x equation and the integral is based on y with respect to y. Okay, but the same formula. So 1 plus the derivative square under the set. Okay, under the set. Okay, for example, this one. Okay, so we find the arc length function. Okay, arc length function. Okay, for the curve y equal to x squared minus 1 over 8 ln x. So you have a curve y equal to x squared minus 1 over 8 ln x. So we are taking, let's say the first, the starting point on the curve is 1, 1. So I'm not sure that the exact curve looks like. Okay, for example, just imagine that the curve is like this. So the first point is, let's say here, 1, 1. Okay, x equal to 1, y equal to 1. So this is the point P naught. Okay, as the starting point. So you want to find the arc length function for the curve. So meaning that your last answer will be a function where you can just substitute the value of x together, specific measurement of length, okay, along the curve from P naught. Okay, from P naught. So let's say you would like to find the length of the curve from this P naught until this point. So let's say this point is maybe 4, 5, I'm not sure. Okay, P1, for example, whatever value. So you can just substitute your x value here into the formula. Okay, so we are getting an arc length function. So how to do this? So first we need to differentiate. So based on the formula, we are given the y equation. So first we need to differentiate. Okay, we need to differentiate, and then we find 1 plus derivative square based on the formula. So we need to differentiate. So we are getting 2x minus 1 over 8. So differentiate ln x, we get 1 over x. So 2x minus 1 over 8x. And then we substitute into this formula. So 1 plus f prime x squared. So this one you need to expand the bracket. You need to expand for each of the terms. So you get this one. So from that one, you simplify everything and you get this one. So plug in into the set function. So you have this one. Okay. So this is your integral. Okay, this is your integral. So the arc length function will be given from the formula. So dx will be from 1, this is 1, until, so we do not have the endpoint because we are finding the arc length function. So we can just assume the last point as x, whatever the x value is. So 1 until x. Okay, from 1 until x. So integrating this integrand, which is the one that we have solved before, here. So from 1 until x, so integrate with 2x plus 1 over 8x. Okay, so altogether we get x squared plus 1 over 8 ln x from 1 until x. So you get, substitute x into all x, and then you substitute 1 into all x. So you get this one, you get a function, you get a function for the arc length, okay, for the arc length. So let's say you are finding, you would like to find the length of the arc along the curve, the same curve, from the same specific point and to point P1 that starting with x equal to 3 and y equal to whatever value when you substitute 3 into the function f to 3f3. So this is x from 1 until x equals to 3. Okay, so we are integrating from 1 until 3. But because of we already have the length function from 1 until x, so you get this. So you can just substitute the x value here into your formula, into your function. So you are getting 8.1373. And again, all the applications that I show here, the area, the volume, the arc length. So you need to remember that the last answer must be in positive value. Area must be positive, volume must be positive, the length of the arc also must be positive. So in case you are getting a negative value, so you know that your answer is not correct. So please check your working steps. Okay, because the last answer should be in positive value, not the negative value. Okay. All right, so any questions so far? No questions. Oh, yeah, we have one in the chat. Oh, Bobby's asking.
Oh, that's for me.
Okay.
Come on, don't be shy to ask and everything about the application of integral. Because next week's our class will learn about this application. So I think it will be good if you know about the basic concept of the application of the integral.
All right, we have one question here. Why the answer is positive? It's not because of the function. It's actually because we are finding the area, the volume, or the arc length. For example, we are finding the arc length. So the measurement, the length must be always positive. So for a function to find the area or volume. So let's say the question asks to find the area or to find the volume or to find the arc length. So the last answer must be positive. But we cannot anonymously do the integration. Not all integral will give us a positive value. Okay, give a positive value. Like what I showed just now. If you do the integration of this, like what I showed just now, if you do the integration of this, you're going to get a negative value. But because you know that the question asks you the area, you know that the answer must be positive. So you need to multiply with negative. But let's say the integration representing the temperature. Let's say you have a temperature function, whatever temperature function, Tx, and then you integrate for a certain value of x1 until x2. For a temperature function, it's not necessary to have a positive value because temperature can be 0, can be negative. So doing the integral of a temperature function might give us the average temperature across that medium, across the plate or whatsoever. But the answer might give us a negative value or a 0. So to understand the question is a very critical, and to know that what to expect for the answer. If you are solving the temperature, so you might have 0 or negative as the value. If you find, let's say the question asks about the total population, the total people living in a city, given a population function. So you know that the number of people inside a city cannot be negative, cannot be 0, because we are counting, we are doing the head count of the people. So the resulted, the last value must be a positive. So let's say to find the number of people living in a city, you get a negative value. So you might do something wrong in your working step. So you need to check it. Same goes to the area, to the volume. Okay, because it must be positive. Yeah. All right. Okay. Any other question? All right, so I keep going. Okay, so some other applications of integral that I do not have enough time to touch in this session. This session is just to give you the overview, okay, of the applications of integral, but we have a lot more applications of integral that relate, which is finding the distance, velocity, and acceleration. So this one, regarding the motion, okay, regarding the motion. So let's say your function fx. So in the previous example, all the fx is a function, okay, a function. Then we reflect it through a graph, okay? So let's say you have a distance function or a velocity function or an acceleration function. So the integration of the velocity, you are going to have a distance. You're going to get a distance, okay? We have a distance, differentiate distance, we get a velocity. We differentiate velocity, we get an acceleration. So this is differentiation. So when you're going backward, so this is integration. Okay, that is for the distance, velocity, and acceleration. Okay, so we also use calculus or integral. We use integral, specifically integral. We use integral to find the surface area. Okay, we have a formula for a surface area. I'm not remember the formula. You can find the integral to find work, to find mass, center of gravity, and also the centroid. Okay, centroid is the center point of a solid. Okay, that have a center point of a solid, or you can find a center point of a lamina. Lamina is actually a thin plate. Okay, let's say you have a box, for example, a solid. So you would like to find the center of the box. So we can use the integral to find the centroid, the center point. Or also you have a ball, for example, a ball made up of a specific metal type. So you would like to find the center of gravity of the ball. So you can use the integral to find the center of gravity. So the center of gravity is not necessary to be the center point of the shape, okay, of a solid. It can be not the center point, but the centroid is the center point. But the center of gravity not necessarily equal to the center point, depending on the shape and depending on the density. So you might need the density function as one of the information to calculate the center of gravity. For the centroid, you need to have the mass or the volume of the solid to find the center of the point. Okay, so these are some of the applications of integral. But for this kind of application, so you might need to use a higher order integral. Okay, but what do you learn today is only the single integral. But if you pursue your mathematics into the more high level mathematics, you're going to learn a multivariable calculus. You can have the double integration, and you can find the triple integration and so on. So to do the double integration or triple integration, you're going to learn a lot more concepts and a lot more technical approach in doing that. Okay, in doing that, just for an exposure to you. The single integration is not the end. We have a lot more kind of integration, okay, using the spherical, using the cylindrical, and so on. So I think that's all for me to share today. Okay, I open up for a question and answer session if you have any kind of question.
Yeah.
No, because
Any question? Sorry, maybe my student side to ask something about this new topic.
yeah, I think they are learning something new. They do not
Yes.
really know what to ask yet.
Mm-hmm.
Maybe during your class next time, they will ask a lot.
Yes. Any question? No? Not at all? Do you understand about the topic of the integral application? No? Okay. Yep. Your time.
All right, so I think that's all for me for this session.
Oh, okay. Thanks for the interesting topic, Dr. Noraziah. Begin with some application of the calculus in medical science. Some engineering topics, right? And for the economic problem. Hope it can motivate our students to learn more about the calculus. And the important thing about the calculus is to improve your critical thinking, right? Hope this session help you to get more understanding in calculus. Maybe it's a new topic for you because in our class we only learn about the basic concept of the integral, but uh, today we have any knowledge about the application of the integral, and next week we will learn about this topic. Yeah. Um, and we know that from Dr. Noraziah that to find an area or the volume of the revolved region, you need to develop the integral formula by yourself. Yeah, start from analyze the bounded of the area, and then you know that the revolved region produces a solid with a radius as a function. So you need to find the radius of the solid, and then later on you may to calculate the volume of the revolved region. And at the end we have a arcus length formula. For this arcus length, you only need to use the formula to calculate the arcus length of the function. And thank you very much for your time, Dr. Noalia. Sorry if my student very shy to ask some question. It's
It's
so
okay.
quiet. It's so quiet. Okay. Maybe that's all for this session. Or any question for the last time for all of Indonesian? Okay, no. Miss Ajeng.
Okay.
Ajeng, come on.
Thank you, Dr. Noraziah and Miss Fiska for today's session. Maybe before we end, we can have a group photo together. All the participants, please turn on your camera.
I'm so sorry that I cannot switch
Mr.
on the
Yuda,
camera.
please help us for
Yes,
the
doctor.
screenshot. It's okay, Dr. Noraziah.
For the first, I think I will take 3 or 4 page. Okay. For the first slide, I will take in 3, 2, and 1. Please smile. Okay. And the second slide. Wait. Okay. The second slide will take in 3, 2, and 1. Okay, and the last slide. Okay, 3, 2, and 1. And after this, I will give you exit ticket so you can fill in and check in the chat box. Okay. Thank you very much.
Thank you, Mr. Yuda. Thank you, Dr. Noraziah, Miss Fiska. See
Sorry.
you again in the next semester. Yes, Dr. Noraziah.
I think we have 2 questions in the chat. Can I address
Oh, okay.
this? Can I address?
Okay.
The students already leaving, yeah?
No, I think they are still in here.
Okay, all right. So the first question is, why do we need to find the outline? So it depends on the application. So sometimes maybe we want to know how, for example, the application of the launch of the rocket. So we would like to know how much the rocket travel through the projection. So you can use the outline formula to know how far the rocket travel. So that is the application, one of the application of the outline. So for the second question, if there are any possibility that the x1 and x2 variable is not declared, if so, how should we solve it? So if x1 and x2 is not declared, meaning that you do not know the exact value for x1 and x2, so when you solve the integral, you are going to get the function, or you're going to get the formula as what I shown just now for the arc length. Okay, so you're going to get the function. So if you have the x1 or x2 letter, you can just plug in the value. So I hope that answer the question to those who asking.
Okay, thank you, Dr. Azia. Anyone?
Another one asking the tips to learn integral faster. Sometimes when I try to solve several questions, I got more confused than to understand it. Okay, for me, I always remind my students, before you are learning calculus, you need to strengthen your basic mathematics first. So like what we have mentioned just now, you want to do the bracket expansion, you want to multiply with the power 2. So all those kind of technique you need to master first before you do for calculus, because calculus is another advanced mathematics.
Yes, I agree with you, Doctor. Yeah. So for also that, please be note, yeah. Before you learning calculus, you need to review more about the basic mathematics, right, Dr. Noraziah?
The algebra and so on.
Yes, right. You're right. I agree with you. Okay.
All right, I guess no more question maybe.
Thank you so much, Dr. Noraziah, for your time. Maybe we can see you soon, maybe next year, or I don't know. Thank you so much, Dr.
Thank you for the
Noraziah.
opportunity.
Yes.
Okay.
Thank you, Dr.
you.
Noraziah, Miss Rizka.
Assalamualaikum.
Waalaikumsalam.